if we were going to write this proof for these Uno cards, we kind of already talked before we started what to write in the first box. So in the first card type, what would you write down here? Yellow 8. That's what we were, what? What's the G word we start proofs with? Given. We're always going to start every proof with the word given. That's the reason, that's the thing we're starting with. They gave it to us. After the yellow 8, what's the next card we can play out of the cards listed? The skip. Why can we play, oh wait, which skip? Because there's 2 of them. Yellow skip. Why are we allowed to play the yellow skip next? Same color as the one before it. All right, we get how to play Uno. After we play the yellow skip, what's the next card we can play? Green skip. Why are we allowed to play the green skip next? Same kind of card, right? So same, we're going to say same letter, just for easy. Same letter. After the green skip, what's the next card I can play? Green, draw 2. Why are we allowed to play the green, draw 2? Same color. All right, after the green, draw 2, what's next? Yeah, the red, draw 2. Because it's the same letter. Okay, what's next? The red 5. Why? Same color. And then after the red 5, I can't see anymore, but what was next? The blue 5, because it's the same number. And once we've made it to the blues, our goal was to get to the blue 1. So can't I play that blue 1 next? And the reason I can play the blue 1 is what? Same color. So do you see how every single time that I said color. Oh, it's my Monday, okay? I know it's Wednesday, but it's my Monday. So do you see how every time when you make a statement or a card type, you then tell me a reason for why we were able to pick that card type? Bless you. That is called a proof. And that's what we're going to be working with today. We're going to be doing algebraic proofs, not geometry proofs. But that's what our notes are about today. So we're going to continue on with the idea of proofs so that we can eventually start writing really, really good geometry proof. But we're going to go back to something that maybe we're more comfortable with, which is algebra and the algebra steps we've been doing, and give proofs for all of those steps. Now there are a lot of properties of equality for real numbers, which are really the fancy names of the things that we've been using to do proofs or to solve equations. Since you started to learn algebra, you just may not know their name. So we're going to slowly go through all of these properties, all of these qualities of numbers, so that we can see maybe the names of all the things we've been doing. The first vocabulary terms are addition and subtraction properties. Now, obviously, we know what addition and subtraction is, but here's what the property states. The property states if A is equal to B, so if you have a balanced equation, and then you add the same number on both sides of the equation, then it's still equal. Or if you subtract the same number on both sides, that it's still equal. This is what our inverse operation steps end up looking like. When we do cross the line, change the sign later with the box method, that is because of this addition and subtraction properties. So if you notice, 5 minus 2 equal to x minus 2, or 5 plus 3 equal to x minus 3. See how on both sides we either have plus 3 or minus 2? That's showing the addition and subtraction properties. That what you do to one side, you can do to the other, and it remains equal. The next set of properties is called the multiplication and division properties. This is also part of what we've always called inverse operations. It says that if 2 numbers are equal to each other, or 2 letters are equal to each other, then if you multiply by some number on both sides, or divide by some number on both sides, as long as that number is not 0, because you can't divide by 0, then we're okay. Then they're still equal. So when we wanted to get rid of a number in front of a letter, we would always divide on both sides. It still lets my equation be equal, so that we didn't break any properties of numbers. So those two right there would eventually combine together to make our inverse operations. So this is what a lot of us would have called it, inverse operations or drag and drop. But it That's not a really good way to read that word. Let me try writing that again with better handwriting. There we go. Those two properties make up what we've always called inverse operations. The third vocabulary word is the distributive property. This one we've probably actually used that word before. We know distribution is where you have a number in front of a set of parentheses and you can multiply it to both terms inside that parentheses. That's called the distributive property. That one we would know the name of because that's the name we typically use for this property. So not a big deal. That one we've got. The fourth property of numbers is called the substitution property. And just like last class when I was not here and you had a substitute, I am gone and someone else was here in my place. So the substitution property is the same. If A is equal to B, then A can be substituted for B in any equation or expression. If it's equal to that number, you can use it. This is how in all of our questions so far, we've solved for X and then taken that number and plugged it in somewhere else. That's using the substitution property of numbers. If X is equal to 7, then you can put 7 where the X goes. That's exactly the substitution property. The next three properties also kind of feel like you're like, well, duh, that's how math works. Correct, because these are called the reflexive, symmetric, and transitive properties. In the reflexive property, it says that A is equal to A, and you're like, yeah, A is equal to A is true mathematical statement, like 12 equal to 12 or 5 equal to 5. That is technically called the reflexive property of numbers, that they are equal to themselves. They are themselves. It's an identity crisis moment. The symmetric property says if A equal to B, then B equal to A. What happened here to go from this equation to this equation? What did we do? Even simpler, it is a conditional statement, yes, because we have an if then, very good. But just looking at A equal B and B equal A, what happened? They just switched. That is the symmetric property. That means when you solve an equation, if you accidentally get the 2 coming first, you've always tried to rewrite it where the X comes first, yeah? That's because of the symmetric property. We like the letters to come first, so it's a good thing we can just switch them. That's with the symmetric property. The last one is called the transitive property. This kind of goes with what you did last time with inductive and deductive reasoning. It says if A equal to B and B equal to C, then A equal to C. It's getting rid of the middleman, like we learned last time in our notes. So if A is B and B is C, then why even bother talking about B? We can just say A is equal to C. That's called the transitive property. It translates from one thing to another to create a new thing. Transitive property. So we're going to practice today just utilizing these vocabularies to talk about why we do different things in math. We're giving a reason, algebraically, for each step in a problem, like you did in the Uno cards. For this first one, we have if x divided by 2 equals 7, then x equals to 14. What did we do to solve for x, going from this statement, the if, to the then? What did we do? You don't have to use fancy math words. Just tell me something. What did we do? We got rid of the fraction. Now, how do we get rid of fractions? What's the opposite of a fraction? Fractions are division, by the way. So what's the opposite of division? Multiplying. Okay, look at the top of your page. What property would we actually list out, not just saying we multiplied? What is the name of the official property that allows us to do that? It's in the red. Multiplication and division property. So that's what we're going to write down here. We're going to say we were allowed to do this because of the multiplication and division property. If y'all are okay, I'm going to shorten property to prop. Are we okay with that shortening? Okay. Multiplication and division property. That is the property of numbers that allows me to do this. I get rid of a fraction by multiplying, because I can multiply on both sides and the equation stays equal. Okay. Let's give a reason for the next one. It says if xy equal to wz, then xy minus 4 equal to wz minus 4. What did we just do here? We starts with the S. What did we do? I think I heard somebody say it. We could say that. Yeah, substitution. See how we substituted a number on both sides? those two segments would stay equal because we substituted on both sides. So that property is officially called the addition and subtraction property. So again, a lot of this stuff you're like, well, yeah, that's how that works. Correct. We're giving the proper reason for why all of this works. For the third one, it says if 2 times x plus 3 equal to 12, then 2x plus 6 equal to 12. Why am I allowed to make this conditional statement? Yeah, we had parentheses and then all of a sudden we don't have parentheses. What is that called again? Distribute. It is multiplication, but it's specifically called the distributive property. That's why we're allowed to do that. It remains equal even after we do that multiplication with the distribution. Okay, fourth one. We have the conditional statement that says if negative x equal to 21, wow, I said like not enough words. If negative 3x equal to 21, then x equal to negative 7. How did we go from the if to the then? I notice that next to x there was a number, and then all of a sudden next to x there's not a number. How do you get that number to go away? Here's what else I notice. I notice that 21 is decently big and all of a sudden it says 7. So I know it's something that has to make numbers smaller. Absolutely, we have to divide it by negative 3. And the property that allows me to do that on both sides and maintain equality is called the multiplication or division property. That's the reason. The next one says if EF equal to GH and GH equal to JK, then EF equal to JK. What's the name of the property that allows me to make that conclusion? I think I heard somebody say it. Yeah, you're pointing at it. What are you pointing at? The transitive property. Very good. That one's like when you cut out the middleman. In our deductive reasoning lesson last time, we did that. Transitive property. It translates from one thing to another. Okay, cool. It says, if JK equal to KL, and KL is 16, then JK is 16. What allows me to do that? I have JK equal to KL, and then KL is 16. So what did I do to put 16 next equal to JK? Let me color code for a second. Maybe this is helpful. If we have JK equal to KL and KL equal to 16, then we can just say JK equal to 16. What do you notice about the colors? We have 2 of each, okay. Let me color code the one above it so maybe you can see some things. EF equal to GH, GH equal to JK, EF equal to JK. What do you notice there? Same colors, yeah? What was the property we used right above this to be able to make that conclusion? Transitive property. We're going to actually give this one 2 properties because we can definitely use the transitive property to make this argument, or we can also use the substitution property. Because if KL is 16, then I can just substitute 16 right here for KL, and JK would be equal to 16. So both of those are fine. They're both good reasons for that to exist. Second to last one, it says ZY equal to ZY. Why are we allowed to say that? The reflexive one, yes, so the reflexive. Seems like such a silly property, but it is a property of numbers that they are equal to themselves, or segments are equal to themselves. Okay? The last one says, if PQ equal to ST, then ST equal to PQ. What's that one called? Symmetric. So that's the one where we can write equations in either order. That is the symmetric property. So these are the official words that you would use to do proofs for algebra. In this class, we've been working with the box method to solve actual algebraic equations. So while a normal side-to-side inverse operations version of an equation would definitely continue to use these vocabulary words to give a reason for each step, we're going to use different words on the back of these notes to talk about the reasons for the box method that would maybe make it more clear for you later when you go back and look at these notes about what we're doing in each step. But the point is, anytime you do something in math, you should be able to state the reason for why you're doing it. That's what we're going to practice on the back. Your classwork today is going to go back to using these words, so the front of your note's going to be really helpful, but we're going to practice writing proofs with language we understand on the back. So here we go. I've set up a box method for you, a total from start to finish box method equation. We're going to give a reason for each and every step. So we write down the first statement. The reason for the first statement is always what? Given. Amazing. Now, if we look from the first step to the second step, what did we do? Algebra. Yes, you're not wrong. We did some algebra. What if I did this with some little arrows? What is that called? Distribution. So the first step in a box method equation is to always look for distribution. And we're allowed to do this because of the distributive property of numbers. We got rid of the parentheses by distributing. Okay, this next step is not going to be a vocabulary word from the front because, again, the box method follows different steps. But the next step, what did we do? What did I do with those things up there? Not math words, just tell me what I did. Yeah, you're going to draw your boxes. And then we also, I already did it for us, but we also made our top boxes. So I'm going to say count top boxes. So our setup step, essentially, we're going to draw our boxes, we're going to count the number of top boxes we need, and make an appropriate number. Does that make sense to everybody? Yeah. Cool. What is the words I've been saying for the next step? How did all of these numbers get where they need to go? Because over here, originally on the left side, it said 3x and 2. And now on the left side, it says 3x and 4x. What happened? Fabulous. She said the ones with the x's go in the first box, the ones without the x's go in the second box. That's an amazing reason. Here's the reason we're going to write down. We're going to write down drag and drop, which is where we will draw our actual arrows and drag and drop the things we need to do. But properties-wise, to actually do this, what we are using is the addition and the subtraction properties. But for our sake, what I've been saying when we did this box method was that's drag and drop. All of the x's on the left, all of the non-x's on the right. But we are technically using the addition and subtraction properties to do that. Okay? What do we do to make these bottom numbers down here? These. How did I get these numbers? We add. So we add both sides. We're going to call that combine like terms. Combine like terms. CLT, if you will. Okay. The last step, what do we always do at the very end of these problems to get our x by itself? Ooh, we've already done the adding, so now we're at this one right here where I got a 7 floating down here. What am I doing with that? I am dividing. So we are going to divide on both sides. Now that's what we normally say, is we say divide on both sides, but that's actually the multiplication or the division property. Because we're allowed to keep numbers equal to each other if we multiply or divide by the same number on both sides. That's why it has to be specifically the same number. And then wouldn't you know it, we get to our final answer. This is what we would put a box around, call it done. This is the fun part for me. In a really advanced mathematical proof, there's a fun symbol that you put at the end of the proof, and it literally just means I'm done. And the symbol is just a box that you fill in. So we're going to put that at the end of our proofs because it's kind of fun. That means the end. I'm done. Technically in Latin, it means QED, quod erat demonstratum, which is not what you have to know. It just means the end. So I have fun always putting that at the end of my proofs because it makes me feel like I did something really important, that it gets a period at the end of the sentence. So do you see how every single thing we've done mathematically has a reason? Whether it's a property from the front page or if it's a reason for the algorithm that we've been using, drawing the boxes, counting the top boxes, it all has a reason. Can we do the bottom ones together, giving a reason for each time we're solving these equations? Let's do this one, number 3. All right, it says given 14x plus 70 plus 20x plus 8 equal to 180. Ooh, that looks familiar. 2 things add up to 180. Bonus question here. If 2 things add up to 180, what kind of angles are they? It starts with an S. Supplementary, very good. One of them would have to be obtuse, yes. Okay. What's the first thing I write down in this proof? The first statement? Given. Okay, good. If we know the given goes here, let's actually write the given statement in here. 14x plus 70 plus 20x, use your nice handwriting, please, plus 8 equal to 180. Our goal is to get down to the fact that x is equal to 3. Okay, what's the next thing I do in the box method? In the one above this, I had to do distribution. Do I have to do that on this one? No. When do you know there's distribution? The little parentheses. Okay, cool. So we can skip that step. We don't need it in our reasoning. What was the next thing I did? Draw our boxes. Okay, so here I'm going to draw my boxes. Pow. Pow. Okay. What else do we do in that step? In the draw the boxes step? Count, yeah. And we're going to count tops. This is our setup step. How many top boxes should I have on the right? 2. How many top boxes should I have on the left? 3. Why 3? Because there's 3 numbers. Okay, something we didn't do in the last problem because it was printed on your paper. We are going to draw a line down the center of our equal sign because we need that for the next step. Okay, we're going to combo 2 steps together because we didn't leave you enough room to do it all the way. If I start doing this step right here, which we've all followed before, we got all of the x's on one side and all of the numbers on the other. What was the red word that I used in the example above this to talk about why I'm allowed to do this? What's the reason we gave for the drag and drop step? I put it in parentheses. So if we look up there, addition and subtraction properties. So we're going to include that on this reason. This one has a lot of things happening. So this is the addition and subtraction property. Okay, it's going to feel weird because I'm going to make you space these out. But I want you to go ahead and draw all your boxes again with the numbers in them because we have to do the next step here. Just like we did in the proof above this. So we write all of those numbers again, but we're gonna go ahead and do the next step. What is the next step after I've gotten all of the things set up on the top and I've done my add and subtract properties? Ooh, we've done the drag and drop because that's how we got the numbers in the top.
Subtract. Combine like that.
Combine like terms. This is when we're going to add or we're going to combine like terms. So it looks like we're adding, but yes, really we are combining like terms. When we combine like terms, 30x plus, 14x plus 20x is 34x. Negative 70 plus negative 8 plus 180. 102, wow. Okay, that was one step. So now we have to show the next proof in the next box. So guess what we're going to do? We're going to draw all those boxes one more time. And put all the numbers where they go because we got to show one step at a time. After we did the combine like term step, what's the next thing that we do? Multiply and divide property. So that is the property we're going to use to do the next step. In fact, well, here's the question. Are we going to multiply or are we going to divide? Divide. And what are we dividing both sides by? 34. And when we divide 102 divide by 34, if you trust me enough, we would get 3. That's what we wanted out of this proof. What's the symbol for the end to show that we're done? The little box with colored it in. It's a fancy mathematical symbol for end of proof. Okay, it's time for you guys to try one on your own. We've got example 4 over there. Example 4 says 15x minus 43 plus 8x plus 18 equal to 90. Ooh, bonus question again. If two angles add up to 90, what are they called? Complementary. Starts with a C. Complementary is the one that adds to 90. So this applies to what we're doing in class. We're just going to look at only the algebra. I'm going to stop talking and I want you to fill out the proof just like we did for number 3 for your equation. You give me both the box methods and the reasons each time. All right, I'm hoping I gave you enough time to finish. Let's help me fill in all of the words. I've got all of the statements written, all of the math side. I need the words to go along with it. So anytime we're starting a proof, what's the name of the first reason? Given. Very good. We got to hang on to that information. Now that we wrote a lot of things in this next box, because we did a lot of things, we had our setup steps, which was draw boxes, as well as count top boxes. But what is the name of the property that allows me to do the drag and drop step? Very good. Addition and subtraction properties. Then we took all of the top boxes and we added them together, which is our combine like term step. I'm going to write CLT for combine like terms. If you ever see me write CLT again, that's for combine like terms. We're adding like things. Put your phone away. What is the name of the step that allows me to do the next to last box here? Multiplication and division property, specifically the division one, but it's one property. The multiplication and division property of numbers means it's still equal on both sides after we divide by the same number on both sides. And then we get to our final thing that we wanted, our final proof, and we put the end box since we need one more reason. That is the end. We have proved that x is equal to 5 using the box method. So like I said earlier, the box method has some weird reasons because it's a non-traditional way of solving equations, but we can still use these property words when we're doing the box method, and that's why we're allowed to do the box method. But the setup steps are not typical words you see in math. So when you are doing your classwork today, you're going to go back to doing problems like the very beginning of these notes on the front, where we were giving a reason out of the table of reasons for each step. So it will look, again, more like the front of the notes for our classwork today than the back of the notes. But here are the reasons for us of why the box method works and when we use it. So your classwork today is on Desmos. I just clicked go on my computer for it to post for you. When you finish this assignment, you don't have any homework. But if you don't finish this assignment, then you do have homework. So while we're working, you'll have to type words in. Make sure you're spelling things correctly because you're giving me correct reasons here. But your word bank is there on your paper. It's going to also show up on Desmos. Those of you who did not finish the quiz earlier, please finish it before you start your classwork.